jump in.
Okay.
All right. So binary trees. So what we wanted to start doing was just talking about some of the concepts you may run into in an interview. We're going to keep it pretty light, pretty simple. We're going to go over the concepts of the binary tree. We are going to actually write some code. We will write some tests. We're going to focus on exploring the binary tree, the binary search tree, and not so much on performance. So we'll write code, but we'll use recursion in our methods rather than iterating through the tree, iterating in the code. Let's see, that's about it. So we'll jump in here and we'll get started. Let's see. All right. So where we'll start is just reviewing the binary tree basics. And I'm going to see if I'm any good at a slide deck. All right, can you all see my screen?
Got it.
Got it. All right. So tonight we're going to go over the binary tree basics. We're going to focus on three things here. So we're going to focus on every node having 0, 1, or 2 children. We're going to have our children will be referred to as the left child and the right child. And in practice, and like tonight, we are going to use the binary search tree specifically. So this is visually, this is a binary tree. As we just talked about, it's every binary tree, we have a root node. And then that root node will have a left and right child. And then those nodes can have a left and right child, as you can see here. There's our root node, it's pretty obvious. And then we have our left child and our right child. You can sometimes refer to the child, right, has a parent node, and the parent will have 0 or 1 or 2 child nodes. You can also refer to them as siblings. We won't get into that so much tonight, but that is the concept of siblings, 2 nodes in the same, next to each other at the same depth or height. And we also have the leaf nodes. So all these nodes down here at the bottom, without any children, those are the leaf nodes on the tree. Let's see, so pretty simple concepts here. We have the height and the depth of the tree. So height and the depth will just depend on from where you're starting. If we're starting at the root node and counting down, then every line we cross down to the bottom node there, set from 20 down to 7, we're crossing 3 lines. So we have a depth of 3. And then if we do the reverse, we go 7 to 20, then we'll have a height of 3. One other thing about we'll get into that. So some of the things, another characteristics of a tree is this is what's called a complete binary tree. So all the leaves are at the same depth. So our 3 leaves at the bottom, 28, 15, and 13. Those are all at the same depth. All levels except the last level are completely full. And for it to be complete, all the levels at the last level have to be stored left to right. So if, for example, if node 13 here was actually the right child of 6, then we would not have a complete binary tree. But because it's on the left, all the leaf nodes are, filling from left to right. And then the last thing here is the full binary tree. All the leaf nodes have the same depth, and then every node except the leaf nodes have 2 children. All right. I kind of blazed a trail through there. I know I have a mix of people who've probably seen this in a computer science course or read about it. Is there any just general questions y'all have before moving into binary search tree.
I
Okay,
think some might wonder, like, what's the efficiency of this, of a binary search tree versus other algorithms?
gotcha. Yep, that's a good question. Why have the binary search tree? So let's get into that. So the binary search tree, like a binary tree, but it has some extra qualities, right? So every left child always has a smaller value than the parent, and every right child would always have a larger value than the parent. You could reverse that if you wanted to, every left being larger, every right being smaller, but the point is that it's consistent, one or the other. Generally, you see left is the smaller value and right is the larger value. As far as efficiency, this is what starts to get us into O log n, because it is a binary search. And what makes it a binary search is because we are splitting the nodes in half here. All nodes on the smaller than the root on the left, and all nodes larger than the root are on the right. And because every node follows this rule, if you want to search for 15, let's say, we're only going to check 3 nodes until we find 15 on this tree. If this was an array, we would have to start at the beginning and step through each value until we found 15, unless we did a binary search on the array. But if you were going to do an iterative search, scan the entire array, that would, it may take you, right, half the array until you find 15. But with the binary search, if we're looking for 15 or we're looking for 20 or 21 or 28, there's always going to be 3, right? 3 nodes to get us to the value that we're searching for. So that's where the efficiency of the binary search tree comes in. Okay. I blazed through there so we could do this, write code. All right. So what are we going to write? Well, we're going to start test driving out a tree concept, and we're just going to start inserting nodes. I'll make sure I can see my stuff here. All right. And contrary to what Joel said, we are going to test drive. But we're going to kind of test drive a little fast. So if we're all ready to go. So the first thing we're going to do is we have an array, and we're going to insert all these numbers into our tree using the iterative approach of TDD. So let's get started. So the first thing I want to do is, I'm going to say I'm going to insert my root node. So let's create a tree. Actually, let's call it simple binary search tree. Okay, we're going to create this class, and we're going to put it here. There we go. And then we're going to take our tree and we're going to, what do we call it, add, or we want to call it insert? Anybody have a preference?
I prefer insert.
Insert, you got to vote. And we're going to insert, what did I say? 20. Okay, let's create a method called insert. And I want to use integers actually, but I made it a string on accident. There we go. And how do we know we have a 20? Well, let's do this. Let's say assert that our tree, find 20 or get. Anybody have a preference?
Fine, sounds pretty good.
20, and it should find 20. All right. Let's use objects. And let's get this passing. Is equal to, that's where we go. All right. As we all know, it's not really doing anything, but hey, there we go. We've inserted our first value and we can find our first value, so we think. So let's go to 25. So now we're going to insert 25. Because 25 is larger than 20, we're going to stick it on as a child of 20. Now we could in TDD kind of force the code into following the nodes. I'm going to skip some of those steps so we can move through building out the tree. So I'm going to do a little bit of jumping where I normally may iterate a little more with my code. But let's go ahead and get rolling. So let's insert the root right child. How about that? Let's see. Let's make that a field. And then let's make this call it setup. There we go. There we go. All right. So I can reuse the tree. So now I need, because I have a fresh tree, I'm gonna have to insert 20. And then I have to insert, what did I say, 25? I'm gonna go look. Yeah, 25.
Yeah, I think so.
Okay. So we have 25. Let's duplicate here. Oh, come back. Come back. There you go. And then if I search for 25, I should find 25. And I can also actually hold myself accountable and say I should also get 20. Although the other test is doing that, so it may not be necessary code. All right. And as we expected, our code is failing because, well, because we don't actually do anything. So let's see here. We could say, well, I'll just return whatever value you give me, but we're gonna avoid that step. So that's one of the TDD aspects I'm gonna skip over. So we're gonna, the first thing we need to do is we're gonna create a root. And so let's make this a simple node. How about that? I'm gonna call it root. I'm gonna create a new simple node and I'm gonna give it a value. Let's create this class. That looks good. All that looks good. All right, so now I'm going to give it a value. Let's promote this to a field. All right, so insert, I'm going to say root. You know what, then I'm going to return root.get value here. Okay, then I'm going to have to store this. Let's see, can I introduce create field from parameter? Yes. Thank you, IntelliJ. All right, so now we've inserted a root and we got our value. I'm gonna run our tests. Okay, so our root test is still passing. It's still happy, but this test is not happy. So we need to give this child, or this root, our child node here. So now that we've inserted this, when the second value comes in, I'm gonna wanna have to add it to, according to our tree rules, because 25 is larger than 20, I'm gonna put it on the right side of the root. So I don't want to keep creating the root every time I come in here. So if root equals null, then this will come here. And then we'll just return. Okay, so let's do this. So root dot set right. Let's just create a new simple node, give it the value. And let's create the set right method. And then we will assign that to a field. There we go. Okay, so that assigns it to the field, but it's not going to get us our test passing, is it? Okay. So let's do this. Let's say if, let's see, if root dot get value equals value, then, well, then we'll return root. Else we'll return root get right dot get value. We don't have a get right, but we'll create that. All right, is that enough? Did I write enough code? Oh, nope, I didn't. There, now we wrote enough code. You know what? I'm gonna be responsible, and I'm gonna get in it. Oh, IntelliJ did that for me, didn't it? Root and one child.
So Nate, I see a danger coming for us. Maybe, I don't know if we need some tests for this at some point, but I presume the value can be null sometimes. So we might have a little bit of a train wreck going there if we happen to start with a new tree and try to search it.
That's a good point. Let's do that. Let's create a null check. So the question is, what if I attempt to insert a null?
Actually, more about if I have a brand new tree uninitialized with any values, will that find throw an NPE on me?
Gotcha.
Wait, you said an NPE?
Null pointer exception.
Okay, thank you.
Let's see. Find can handle nulls. Well, there's two cases, right? There's find can handle giving it a null.
Yeah, good.
Right. And actually, I don't need that line. I got a line here. We can say is null, keep our lives simple. And it cannot. IntelliJ, please run all of them. All right. And it cannot handle null. So let's go in there. Nope, not you. You. So let's just let's do a check. We'll just say if value equals null. And 5. There we go. Nice. All right. So that was a good call out. We can now handle null in that regard. We could also say maybe we don't want to allow a null to be inserted. We'll come back to that. All right. So we're now inserting our right root child. Let's go into doing the left child. And then we'll have a root with 2 children. So let's see, it's root left child. Okay. So we did our 25. Now we're going to go to 6. And because it's 6, it's going to go to the left side of 20. Okay, so now we have some decisions to make. I'm not going to keep repeating myself on all these tests. So what I'm going to do is this number. And then I think IntelliJ wants me to do that. Well, that didn't work. I'm suspicious of my code. Let's try that again. There we go. That's what we were expecting, a failure. Okay. So it's just letting us overwrite the right child every time. It's not actually keeping both children, which actually makes a good case that checking for all of these values is to our benefit. So let's do that. Okay, so I suspect because we're only saving, if our root's not null, we're always sticking our node on the right side of this node. So we need to actually be a little smarter and decide where it should go. So let's keep that one for now. If root value get compared to value, right? If root is greater than 0. Oh, thank you, Null. Thank you. Good call. All right. So if the value coming in, if our root is greater than the new value, we are going to place that value on the root's left side. So let's do that. If root is less than, what did I say? This is hard. If root is greater than, if root is greater than the value, then the value goes on the left. If root is smaller, it'll go on the right. I think that's what I wrote, but that's not what I said. Okay. Okay. So I created a method, but I didn't do anything with it other than break it. So let's call this left. I could have had IntelliJ do this, but I didn't. Okay, else we're going to put it on the right. We can do an else here because, well, because we haven't checked for what happens if we're inserting the same value more than once. But also, we're only worried about root, and we've already assigned root. So there we go. Now, we've got it in there, but we're not actually looking for it. So now we're actually going to start our binary search. So same principle coming in as our insert. We're going to get the value of root. We're going to look at it. Say if you're, same thing, if it's smaller. If root is greater than the value coming in, then we are going to return the left side. Get value. And let's create our method. We're going to return left. There we go. We already have an equals up there, so we don't need to do another. We can just assume since it's not equal and it's not greater, it's going to be less than. And we can return that. There we go. All right, so we have a root and we have 2 children. Easy, right? For now,
Nothing to it.
nothing to it. Okay. Made our commits. We've got our child. All right, so we've got our 2 node. We've got 3 nodes now. We have a depth of 2, height of 2, and we are technically a full, right, complete binary tree. Pretty simple one, but let's move on. So now we're going to insert 21. So now we're getting a little more complex. So now we can't just drop 21 on the root child. We've got to actually go find where 21 is supposed to go. And it's supposed to go to the left side of 25 node. So let's go do that. Let's create a test. There's a pattern developing in our tests. We'll worry about refactoring that later. So what am I going to call this? Insert. I mean, we could call it insert 21.
Grandchild.
Grandchild, yeah. Yeah, insert root grandchild. I like it. All right. Is that going to make it fail? It does. There's another thing going on here that we haven't done yet, and that is asking our tree how big it is. Maybe we'll do that after we take care of this grandchild. Okay. So we're inserting a grandchild. Let's go do that. Now, so we already have the code that checks which way this should go. But every time we find a node, we actually have to run this code again. So this is where we can do, there's 2 approaches. There's the recursive approach, which is what we're going to use tonight. And there's also the iterative approach, which is a little more complicated to write. Recursive is easier in this case, but it's also more memory efficient, right? Because if we have a massive tree, we're not creating this massive call stack of recursive calls. So let's get started. So this is the piece that we want to call. Every time we find a node, we're going to actually, if there's not a space there, we have to go into that node and then look for space to insert our new value. If anyone is not real familiar with recursion, we will take some time here to go over it. So please feel free to ask any questions you have as we go into this. So what I'm going to do is I'm going to call this method. Let's extract this out. And I'm going to call it insert. And I already have an insert. Yeah, I know. Thank you. Extracted. Yes, you're done. Thank you, IntelliJ. And I want to do this on whichever node I give it. I want it to check to see if it has a place for that node. So what I have to do is actually give it the node, my starting point, which is root. And let's add a simple parameter. Let's rename this back to insert. Okay. Doesn't quite get us to recursion yet. We're still failing, but let's see what's going on. So now that I'm in here, I can check, hey, let's walk through our tree. So we've inserted 20, 25, and 6. We're now sending 20 in. So the first visit 20 has is at the root. So we have to decide, okay, am I bigger or am I smaller than the root? He is bigger, so we're going to go here and realize, well, we already have a node. So then we're going to compare this node. Is 21 bigger or smaller than 25? And it is smaller, so it's going to send us to the left side. So let's do that. So we're in here, and we're going to ask ourselves, is this, let's see here, let's compare. So the first thing it's going to do is it's going to come to the right. Let's call this, I'm still looking at this .root. I actually want to look at node, because I no longer want to look at the root node. I want to look at the node that is given to the method. Okay. So the current node I have, which is, we're starting at root. I'm going to look at this because it helps me. So we have a 20. I'm going to have 21. So I'm bigger. So that means I'm going to come here. However, there's a 25 sitting there, so I can't set this value anymore. I have to be a little more intelligent about it. So if node, let's say, has right. If node has right, do something else, do something different. Let's do that. So if I have a right node, then I don't want to just set the right. So if I have a right node, let's create this method now. What is my, there we go. Has right. Well, how do I know if I have a right? If right is not equal to null. Okay, so if I have a right side, what do I want to do? Well, I want to actually insert this value I have then on node dot get right. I'm going to give it the value. All right, is that enough? Nope, that's not enough. Let's see where we're failing. So we're still failing at 21. Well, because he doesn't know how to do that yet. So find has to do the same thing. Okay, so we're going to follow the same concept. So what we did here was we took our base method that started the process, and rather just operating on the root node that we had, we created a method that will take any node that we give it and perform that same operation. And that's what allows it to call itself recursively. But we also have to do it on the find method because it has to know how to do recursion as well. So let's extract this. So good enough for me. Let's say root. And then I'm going to add that method. And I'm going to name it. I'm just going to overload the method. And then I'm going to call this node. And then, oh yeah. Do you want to remember multi-line edit in IntelliJ? I can't remember the keyword for that. Multi-caret.
So what was the magic you did to get that dialogue there?
Control-Shift-A.
Control-Shift-A.
Yeah. And there's a way to do this, but I can't. Okay, whatever. By the time I find it, I could have just done this. So here we go. Okay, I'll get them all renamed. Okay, it's still using root. I don't want it to do that. I want to use this. There. All right. Yeah, I can't remember the multi-line edit. It makes life easy sometimes. Actually, quite frequently. Okay, so we've extracted this out. So now that we have find extracted out into a method and we can tell it what node to search, we can now continue comparing this. So if we're here, we're saying, okay, if we're equal, we're going to return the value. If we're not equal, well, what are we going to do? If the value, if it's on the left side, before we actually call get left, actually we're looking at, yeah, we're looking at the left side, right? Yes, the left side. But first we have to go to the right, and then we have to go to the left. Very good. So if this is greater than our node, which it is, we aren't going to return the right node's value. We're actually going to find we're going to search that node for a value. Is that enough? That is enough. Our tests are passing. Okay. Any questions there before we move on? Feel free to ask any questions, especially if you haven't seen these concepts. Please, please ask.
You can always pop a question into the chat as well, and I'd be happy to read it for you. But you're welcome to come off mute.
Can you go through the last step again?
Mhm. Yeah, absolutely. So starting with the insert. Okay, so do you want to go through just the recursion, the recursive method itself?
Yeah, define method that you added.
Okay. Mhm.
Something. Can you just go through what change did we made?
Yep, absolutely. So this right here is where we changed it. Actually, no, this is where we changed it. So the original code looked like, I'm just going to copy that. The original code looked like this. And so what we were doing is we were coming in here. We gave it the value of 21. We said find 21. It starts with the root node. And the original code was saying, well, 21 is bigger than 20, so just return the right child value. So the change was to replace that, just return the right child value with, okay, the value is bigger than our root node, so do the find again, but use the right node and look for this value on the right node. So then rather than just returning this value, the first call, we pass 20 into the find method, the 20 node. Then we pass, seeing that 21 is bigger than 20, we pass 25 into the find method. 21 is less than 25. So what's the find method doing? Well, it's actually still just returning the left node value. We haven't given it enough code to break it. So it's coming in here and it's saying, okay, 21's bigger. Then it goes to 25 and says 21 is smaller. So just return the value of the left node. It doesn't actually travel down to 21. So we're going to need some more tests to actually force that behavior. Does that make sense?
Yeah, that makes sense.
So right now, if you added a left node onto 21, it wouldn't, the code wouldn't actually be able to reach that far.
You're on mute.
I'm sorry, I had someone here needed help. Could you repeat that question? I apologize.
So the code right now would be, I guess, would the code be able to travel to a, all right, sorry. If there was a left node on 21, if it had a left child, I guess,
Mm-hmm.
would the code be able to reach that left child, or would it just return 21?
That's a good question. So if we were to create a left if it, oh, if the left node was on 21.
I mean, I guess you can't really have a left node, but like with your numbers,
We-
can you?
We could add a left node and see what happens. So a left, oh, you're right. No, we would have to change 21. And we could do that. We could write a test to see what would happen if we 20.1. No.
Insert a 22 in front of the 21.
Yeah. Insert a 22. Oh yeah, good call. So if we were to insert a 22 in front of the 21, would this work? I don't think it would work because I don't know, it can't actually navigate down the left side of a node yet, down the left side of a tree branch. Yeah. So it's still stopping at, it's still stopping here.
Yep.
And when it says, yeah, and it says, oh, this is smaller. So it's just pulling the value rather than navigating down to it and returning the value. So that's our next test. So we could do that here. Actually, since we are here, let's just do that and keep this as is. Is it great grandchild?
Yeah.
It's a great grandchild. Okay. All right, so now we gotta do a little more logic here. So in the find method, yeah, so the find method can't actually travel down the left node right now. So we could fix that here. You could say rather than just returning the value on the left side, actually go into the left side and look for the value. And is that enough? I'm guessing, well, not without that. All right, we're getting null, and that's probably because it also can't do, it has to do it up here too. So in order to insert there, we actually have to, we have to check up here. Does this have a left? Return, no. And I'm going to leave this in my else. I'm just going to mirror the other code for the right side. And then I'm going to insert to node get left value. All right, does that get us where we need to be? It does. All right. Does that make sense to everyone? How that now works?
Yep.
Anyone else want to go over that again? Feel free to ask. It's no big deal. Oops. Now, anyone think that if I start adding code for this, that it'll break or it'll succeed?
How you going? How you going? First, hello.
Hey, Nick. Hey, Nick.
Hi. I did this about 30 years ago when I learned this, so showing my age. Is this a good way to set up a binary list? I'll set up a list to already search in a binary manner. Another way to do it.
Is it a good way to set up a
Like
binary?
Yeah, like setting up this list with all the set rights. Is there an easier way?
Probably. You mean like a more code efficient way to do it?
No, I'm just thinking, well, you know, binary search works with a sorted list. Has to be a sorted list, right?
Mm-hmm.
So
Oh.
if you had a sorted list,
Mm-hmm.
what's the pros and cons of going, hey, let's go and sort this list and not worry about writing set rights and set lefts. All we need to do is go and
I
find
got
it.
you.
And,
Why
yeah.
use a tree if you can just have a sorted list?
Essentially, that's it. Yeah.
Yeah. So it's going to get into the as we get massive amounts of data.
Yep.
So the idea is the tree is not having to resort itself every time I insert a record.
Yes.
But if I wanted to maintain a sorted list, that means every time I insert a value, I have to sort it, right, and go find its place and put that value. You're kind of doing the same thing, but then you also,
Yep.
the list will be backed generally by an array.
Mhm.
So it's not just a matter of inserting, 15, well, let's see what value. So 15, right? It's not a matter of inserting 15 between 6 and 20. It's a
Mhm.
matter of, I also have to shift everything to the right in the array. So 15 goes in the right spot.
This is a wonderful segue and forecast to 2 weeks from now when Nathan walks us through resorting to sorting for interviewees.
Yep. Thank you, Joel, for the plug.
That was the Nick planted that question 30 years ago. So in 2 weeks, Nick, you can come back and you can hear all the mysteries of sortedness in an orderly fashion.
Yeah. Yeah. I'm going to say, I wanted to put myself out there because, it's okay to ask what might be the naive question.
These sessions are set up to learn. And the only way to learn is to ask silly questions. That's why Scott is here.
Yeah. And that's
Yeah,
why we
silly
If your
questions.
question's silly, Scott will ask a sillier one. Like, why did we pick that font?
Right. Right. Exactly. Thank you, Nick. That's a really good question because yeah, it unpacks some of the advantages. I'm not claiming to be an expert on the efficiency of these, but I know not having the backing array, and you still actually could have a backing array with a tree if you wanted to, but okay. So let's do this. I'm not sure that we can make this break anymore by inserting more nodes, right? So let's just build a full tree. We're about to find out. So we're gonna come in here. We're gonna grab this chunk, and I'm gonna go back. What do I need to do? I need to do a 2 and a 28, and that's gonna fill things out. So 15, 2, and 28. See, multi-cursor right now would have made my life easier, but I can't remember the command.
Somebody posted it in Slack.
Nice. Did they?
Are you on a Mac or Windows?
Windows.
Alt-Shift mouse click for Windows.
Alt-Shift mouse click.
Option-Shift mouse click on a Mac.
For IntelliJ? Oh, come on.
Apparently, yeah.
Alt-Shift.
Nada.
Oh, it's because it's mapped to my move line. That's why. It might be a mapping issue. Okay, the quest continues. The coding continues. You know what? Create full tree or fill tree. There we go. All right. And yeah, I think we're good. I think we've inserted, we can build out a tree now. There's a couple of things that it won't do for example, what happens if we want to say no duplicates? Let's just say it doesn't allow duplicates. Can't have apostrophe. So let's build a full tree, and then we're gonna insert 6. And how do we know? Huh? Because that's still gonna pass. I'm probably gonna have to do something like is equal to what? Does anyone know how to calculate if you know how many rows, how deep a tree is, how many nodes are in there?
You have to traverse it, right?
Well, if it's full, it's what is that? 2 times 2 times 2 minus 1, or 2 times 2 plus, yeah, right? 2 times 2 is 4,
Yes.
times 2 is 8, minus 1 is 7.
I saw someone with a master's in mathematics show up just a second ago. Maybe
And they
that
left.
person can weigh in.
They left quickly. So there should be 7 nodes. So if I, whoops. Our tree
Wait,
should
won't there
be,
be 8 because of the extra 22?
the extra 22.
Remove that.
Yeah, we removed it on our full tree. I think we did have it. Where did we have it? Oh, we did the 21.
Seeing that Marcus probably took this class
Yeah.
the most recent, he may be onto something.
Oh no, I just because I asked a question that added an extra number to his the tree on the slide deck.
All right, we're gonna get a little TDD going here. Doesn't allow duplicates. Well, it says it works. I don't know if I believe it.
Well, because your fill tree has 8 values in it right now, even without the extra insert.
It's because I keep getting that double. There we go. Thank you. Okay, so this says it's working. I don't know if I believe it. We're gonna have to challenge the code a little bit. How should we do that? Well, we could insert a couple of values.
What if you just started with one
Yeah,
node?
let's do that, right? So let's say, let's grab our tree. We'll grab a couple values. There we go. It's null. That was not expected. Fine, tree size.
Oh, well, you're
Oh, build full tree is failing. Because did I delete all the 28s? What line are we failing on? Where's our test? There's our test. Yes, we're failing on 28 because I'm no longer inserting 28. This 28 is not, it is in the tree. 3, 4, 5, 6, 7. What did I screw up?
Have you been doing little tiny commits here? Nate?
Yeah, occasionally.
He-
Oh, 22.
The
That's
answer is
that's the the gosh, Nick. What do you... There we go. Nope.
I can always do Control Z as well.
Yeah.
no. And do you want to sequence
Gosh.
till next time?
Nick
I mean,
is,
you're hitting hard. You're doing really well.
yeah. What did we screw up? I screwed up. What did I screw up?
Not going into plumbing.
Not going in the plumbing. What is... Look at that. I'm sorry. You've gone as far back as you can undo. All right.
It is 9 o'clock, and I don't know how long you wanted to go, Nate.
There, we're running again. Oh, it is. It's 9 o'clock. All right, anyone? Thumbs up for keep going? Can't see.
I would agree. I would say keep going only if John commits to using his masters in mathematics to help us understand this algorithmically.
Yeah. All right. I'm going to commit this, even though there's a wonky test because Nick's making me.
Free country, man. It's free country.
Okay.
Nick's paid by the commit.
Well, that makes sense.
He's like
Yeah.
a dog catcher.
Wasn't there a book written by Kent Beck about you must commit every single character, something like that?
Okay.
Your simple binary search tree doesn't it have the size? I think the size method is just returning 7 though.
I think it's just returning a constant.
It is.
Yeah, that's
Yeah,
20
right.
22 is the culprit. I got him out of there. All right. Yes, you are correct. It is in a noble TDD fashion. It's doing exactly what we asked it to do.
Mm.
It's turning 7. Okay. So let's fix that.
If you make it 42, it's complete.
If we make it 42, it's complete. Yeah. Okay, cool. Let's see. Well, I could say that should be 1 and fail.
I don't like that back.
All right. Okay. Well, let's start keeping track of stuff. When I insert something, I could just do this, right? I could say size plus plus. Let's try that.
Cheater.
Why? How's that cheating?
If you have to rebalance your tree or remove something from it.
Our tests don't say anything about rebalancing.
Nick remembers that from 30 years ago. He had to switch the punch cards around, right?
Right? Okay. So this passes, but I'm just going to drive out our size here. I'm not going to create a bunch of tests for it, but this doesn't pass. It says it should be 2, and it's right. It should be 2. Let's do this. It actually should be 2 because I've only inserted 2 nodes. So our code is actually right there. But if I attempt to insert a duplicate, it should remain 2, but it is not. It's going to 3.
Because you're incrementing always.
Because I'm always incrementing. Yep.
You're always
Okay.
be.
Well, I know I have to, if I get a root, I know I have to increment. So if I come down in here now, the only time I should increment then is on insert, right?
Line 17.
Line 17.
Where do you actually
Here?
set the value?
Like this?
It's probably wrong.
It's probably wrong. Well, it was Joel's idea, so yeah. Expected 2, but was 4. Nope. I'm going to say where we actually set the value.
I was wrong.
Well,
Someone
getting
else knows
close.
how to do this other than you and I do.
Yeah. Yep. What's going on here?
I think NC probably
Expected
knows.
2, but was 3. I mean, we're kind of back, right? But what are we not? What are we not doing?
The root node.
Root node? We're
So
not
does
actually.
it set size to 1 when you increment it? I don't know.
So which test are we
Yeah.
running?
No. Get that. I'm sorry, Nick. What was that?
Which test are we running? I got a bit lost. Are we running all the tests here or just?
Yeah, it's running all the tests.
And it's failing on don't allow.
Yep, it's failing right here. So I'm trying to insert a duplicate and I'm challenging the tree to maintain a size of 2 and not insert the duplicate.
Is six
Um,
is probably getting added at the same time. Can you
Yeah,
break through 6?
so-
Debug through 6?
We need to just check, hey, does this, I'm just gonna do, does this equal value?
Don't do anything.
Don't do anything. There we go. That works. Anybody remember the delete tilde? Whatever. Just not allow duplicates. Now that Nick's here, I'm going to commit more. There we go.
Oh, never looked at
Nick must
there you
have
go.
a lot of disk space on his computer.
Is-
Several kilobytes.
So there we go. We can insert, there's a lot more to this. So there's this, well, wait, Nate, that's just integers. What if we want to do this? What do we do? I'm going to create that test. Actually, I'll just start. I'll keep it simple. 4-3, but
Are you about to do wizardry?
yeah, what do we do? How do we get our allows for strings? What am I going to insert? I want to insert G. Well, that's not going to work. All right, so to insert G, I can't do this anymore. I got to do this, right? And then if I come up here and if I do that, then I got to do this. And then I've opened up a whole can of worms. Let's see. Simple node doesn't take a generic, so I'm gonna have to do this. So,
Assuming that they're type homogeneous.
what's that?
Say that again. That was a really smart word.
Are we assuming the type is always the same? Or are they allowed to insert multiple types?
Oh, that's a good point. And we're actually gonna kind of unpack that a little bit. Okay, let's make this a type because we're gonna quickly run into a problem. Not that we haven't already, but
You're making generics
I'm
at
making
9:10
generics.
p.m.
Yeah, we're doing it. We are doing it. Does that look good? That looks good. Value wants to be generic. And wants to be generic.
Your return type needs to be generic too.
That one is good. This one is not good. This one is not good. There we go.
And you probably need to
Getting-
constrain T to make sure it implements the comparator.
Yep. There we go. What's he complaining about? Get value T's object. Now it's happy. Yeah. So can we can no longer do this. So if I want to keep doing that, is it comparable? Is it comparable? Is that right? And
I don't
the
think
node
so.
will have to do comparable. I think it.
Implements or extends?
There it goes. The
There we
node,
go.
I think he's practiced this, Scott.
Oh,
Okay.
Hey,
yeah.
question.
Well, I have been interviewing, so.
Question time, because there's some non-Java programmers here. I think it's kind of similar to .NET, but what are we doing with extends? What? Tell us about that. Or can
Good
someone
question.
tell us what's happening with extends comparable?
Yeah, so because we are doing this down here, we are actually using compare. And compare comes from the comparable interface, the ability for an object to compare itself to another object. That comes from the interface. So any object implementing comparable, you can call compare to. Coincidentally, both string and integer. And so if we go into the integer class, we will see that integer implements comparable. And then if we go into string, string also implements comparable. So now we have a base class that both of these two classes both implement the same interface comparable. And since we want to actually use that method compare to, we have to instruct our class to only accept classes that implement the comparable interface. So that's what allows us to use. That's why we put this here. And that allows us to use the compare to down here. Otherwise, if we don't put this, it's just object. Any object can go in here, but object does not implement the compare to. So that is why we use the generic, and that is why we have to instruct our generic to extend a specific interface.
So basically any generic that extends the comparable class will now be able to work in here.
Yep.
Okay.
Right. So anything implementing that interface, or any interface that extends the comparable, or any class that implements comparable, can be used here.
Are you going to
So-
submit this to OpenJDK?
Yeah, I think so. I mean, I don't know. I think our tree's pretty efficient. We could, yeah, we could. So does this work? So if I did KDH, can I? KDH, KDG, K, doesn't matter too much. Insert that, tree dot size is equal to 4. That seems to be working. All right, so now we're a little more flexible. We can stick different kinds of objects in there.
Can you do it with a character?
Let's try it. We don't accept multi. Actually, we do, right?
You do. That was a trick question.
That was a trick question.
Could you put an integer, a character, and a string in there?
Good. Could we? No, because
They can't be compared to each other.
yeah,
That's right.
we are not. So right now, I think it's doing, actually, thinking about Java, I'm kind of wondering why it's not complaining at me. Because I haven't actually told it what to use here yet. It's just taking the first thing I put in and accepting that as the type.
Well, that failed because at runtime, it's trying to compare two things that can't be compared to.
Yeah, so if I did this.
Yep.
So if I force that to be, then what I'm gonna have to do down here is create a new one. And then if I wanted to do characters, right? So now I'm forcing the issue that no, you can only Now I could pass an interface. I could pass in comparable,
But now you're gonna have the same problem.
right? So yeah, so now you can declare any type that extends comparable you can use here. We're not going to get into multi-types.
There's a really good book to read about that, Java performance, to get really nerdy.
How do we know it's a tree behind the curtain? Asked Nick. Right? I think this is a good question. How do we know it's a tree back there?
Do you care?
Yeah, I mean, we kind of trust the JDK, right? When it tells us, yeah, it's a tree. It's a red-black tree. Trust us, right? We kind of do. We can go read the code, but I know the TDD and everyone wants to know, right? We want to rip the guts out of the class and look at the organs and make sure the one node is pointing to the right node. And there's actually some other ways we can do to challenge our tree. So one thing we could do is find the minimum value in a tree, although this isn't gonna challenge the tree a whole lot. In our binary search tree, the minimum value is always the node that's furthest to the left. So if you travel down the left side, starting from the root, if you follow down to the left children, you will reach the minimum value in the tree. And then the same is for the maximum value. If you travel down the right side of your tree, you will find the maximum value. And we can actually implement that real quick to see it. I'm just going to call it find min max. Did we commit, Nick? I can't remember.
Yes, you did.
I lost track. So, what kind of got lost in?
And all
Is
the
this
code
important?
flying around.
He's
Well, I
looking
can't-
for the min value.
Is that
What's the use case for that? Why do you need the min value?
so why are we doing it? So
Yeah.
we're kind of exploring our tree a little bit. So the easiest, so two easy ways to explore a tree is to ask it, hey, what's your minimum maximum value that you have? So that's a real easy approach. So in this case, right, our min value is 2. Right, we're going to kind of have the same.
T.
Thank you. This is why we ensemble program. Because when it's late and I've been coding a while.
You just want
I
to go
got-
left.
Yeah, go to. What's that, Nick?
I was going to say I like mob programming of it.
We prefer quartet or barbershop quartet.
You know, I'm going to check for null.
Someone sings
Okay.
on linter.
Let's get back to the problem at hand.
Do you mean
All
the
right.
left hand?
There you go. All right, so what do we got to do? Well, we're going to just follow down the left, right? So let's see. While node dot has left, let's say node equals node dot get left. And then we're going to return node get value.
Yeah.
So we are not actually using recursion here. We can actually move this back up if this works. We don't need another method.
Is equal to capital T.
That's why Joel's here. Yeah, let's move this out of here. We actually don't need this. Let's see. We don't want to reassign root.
So node equals.
Yeah, we need this. Copy paste programming. You know it's getting late.
Pays the bills.
Pays the bills. Okay. So now we've just, every time if we have a left node, we're going to go to the next left node. And if we still have one, we're going to go until we don't have a left node. Then we're going to return that value. And that is our minimum. So that tells us, okay, maybe. Are we convinced? Do we still know? Is this enough information to know that there's a tree? Let's see, now we have a max of 28. And we're just going to go the other way. Right? And T. And copy paste, pay the bills. What are we going to say? We're going to say has right. We're going to get right.
All right.
I'm surprised no one sang the
And-
Beyonce song. To the left, to the left.
Oh boy.
All the values in the node to the left.
Give it time, Joel. Give it time.
Tough crowd tonight.
Are they still here?
There's at least 9.
Okay.
It's a binary joke.
It's a nice. All right, so I don't know. We might not be convinced that it's a tree. So there's something that we can do called traversal. We might just do one traversal tonight and call it good, but well, I don't know. It's only 9:20. We got all night. So the in-order traversal. So in a binary search tree, we can actually visit every node in the tree. And we can visit those nodes in ascending order. And this in-order traversal can actually be reversed, so you can get descending order. So the way the algorithm works for a traversal, for the in-order traversal, is we traverse the tree to the left, much like we did for the min, right? We went all the way down the left and we found the min value. And then when we found the min value, that's called the visit. We visited that value and we returned it. But what this algorithm does is it's going to travel all the way down the left. It's going to visit the 2, and then it's going to go up and visit the root, and then it's going to go down and visit the right side of that node. And it's going to do that until it goes all the way through the tree. Okay. And what that looks like is this. We're going to start at the 20, and we're going to travel down to the 6 because it has a left side. 6 has a left side, so we're going to travel all the way down. 2 doesn't have a left side, so now we're visiting the node and we're going to capture it. And then we're going to travel back up to 6. And we're going to capture that because the algorithm says we visit the left. And once we visit all the lefts, then we visit the root. So now we visited 6. So now we're going to go to the right. And we're going to visit 15. So this is called traversal. And then we go back up. And then we're going to visit the root node. And then we're going to go down the other side. And then after this traversal, the nodes have been visited in ascending order. So we've gone through every node, and we do it through every node in ascending order. So let's do it. Does that make sense before I start coding that?
Makes sense to me.
Okay,
But Insia can teach the next section on this.
yeah. I want to capture this. All right. In-order traversal. So let's do it. Let's see, I don't need that. Oof. All right, so what I'm gonna do, I'm gonna assert that tree. Let's call it in order. And that is equal to, what are we gonna do? We're gonna say new integer, right? And we're gonna give it that. So when I call in order, I expect probably have to do this number.
Yeah, and I don't think is equal to is going to work.
Don't think so?
No, it's going to be 2 different memory segments. You need a different is equal to. You need something that says is in the same order. Could be wrong. It's been a while.
Could be wrong.
Find out.
Actually, we'll challenge that.
The integers will be the same, but the array will be dimensioned differently. It'll be pointers to pointers.
Okay. And there we are. So in order, a collection of objects. So can we do, let's use a list. It's backed by an array, or an array list is. All right, so it's late. So I am gonna cheat tonight. Coding in front of everyone is exhausting. Here we go.
You're gonna
All right.
copy and paste in your code?
Nope. I'm gonna do most of it by memory. All right, so we want a list of values. There's probably a better way to do this, but this is what we got tonight. So we're gonna create an array list. Now there's a key that's because we are using another array list. The way the array list works is it goes out there and it creates an array. And then as you fill it, when it fills up, it has to expand that array to take more values. So one of the shortcuts we can take to prevent our array from resizing behind the scenes, because we don't really, the array doesn't know how big the tree is, we can actually tell the array how big our tree is, and that will make this array more efficient. So side note, so now we're going to say if root is null, then just return values. Else. Okay, so in order. So now we're going to traverse our array. So we are going to start with the root, and we want it to append everything to that array that we're giving it, or rather we want it to insert into values. Okay, so now, so the way this is going to work is we're going to look to our left, and if we have something on the left side, then we actually want to go into that node and then do the same thing. Does that node have a left side? And if it does, we're going to keep going down. So the first thing we want to do is say, is this node, does it have left? If has left, then let's say in order. Get left. And we're going to give it our values. And then once we've checked the left, if we don't have a left, we actually want to say values.add get value. So the algorithm looks left. If there's nothing on the left, you visit the node and we're going to add the value, and then we're going to look to our right and we're going to start the whole process over. If it has a right, then we're going to say in order and stop doing that. Tell J. We're going to get the right. We're going to get the values. Is that it? Did that work? It says it worked. Anybody believe it?
I believe it.
There it is. All right, Joel, let's
That's
do
weird.
the integer swap. I know. And when Nate has working code, it is strange. That is true.
It worked.
It is working.
We'll print you off certificate. Can't encoder certified coder.
Nice, huh?
Incio, will you sign it?
Does that really tell us that this is a tree though? I mean, like anyone can sort an array of numbers, right? Like, how do we know it's still a tree back there? Well, there is another thing we can do called pre-order traversal. And this is something we'd use to actually make a copy of our tree. The algorithm is same 3 steps, but we're going to change the order. So at a pre-order traversal, you visit the node and you go to the left, and you visit the left, and then you visit the next left. And then you're going to come back up and you're going to look for the right. You're going to visit the right and you're going to come back up. So we're going to follow the same pattern, but when we visit the node changes. So it's no longer in ascending order. what you get is if you were to now take these values and insert them back into your tree, you'll end up with this exact same structure. So that is what the pre-order one we can use for other things. But implementing this also tells us, okay, even though I can't look at the nodes and make sure things are looking right, looking left, this is challenging our tree, right, to actually behave like a tree a little bit. So let's do it. Let's do pre-order traversal. Or, yeah. Anybody know what I'm going to do to get this? It's actually pretty easy. Recursion is very easy. If you really want to challenge yourself, don't use recursion. Do it iteratively.
Ask yourself that tomorrow.
Yeah. All
No
right.
one, no one gets the binary recursive jokes.
Just keep asking. Just keep asking.
The recursive interview is the next section.
Is
Nathan
that-
will ask, how do you balance a tree? Well, how do you balance a tree?
No, how do you balance it? Okay, pre-order. Okay. Let's see, run it. Like any good TDD would do. It's, oh, it's not null. Okay. Okay, so we're gonna kind of do the same thing. We've got this same basic structure. I'm gonna save us some lines. All right, same basic structure. We could probably refactor, start making this look a little cleaner, but we're still just gonna blaze through here. T, there we go. Actually, I want a little more flexibility. So the same thing, I'm gonna create a pre-order recursive method. There we go. Let's see the node. All right. This is actually really easy to implement because remember the logic's all the same. But it's in a different order. Whoop, don't move things. I'm gonna go back to our logic. So the steps is we're gonna visit our route, we're gonna traverse to the left, and then we're gonna traverse to the right. And we've already got all the logic to do that right here, but we're gonna visit our node first. And then we're gonna traverse to the left, and then we're gonna traverse to the right. And we're gonna run our test.
Help.
And I know what's happening. Anybody else know what's happening? This is when copy paste programming loses its.
You copied and pasted the
You
wrong
lose.
test.
Yeah, you start losing your bonus.
It comes out of Nick's bonus first.
Oh, that's right.
That's 2 story points, Nick. You've lost.
There we go.
I told you to keep checking in.
No, you said commit. You never said anything about checking it in. There's a difference, Nick. You must be a project manager.
Yeah.
Okay.
Update your Gantt charts, Nick. This is Gantt encoders.
There we go. There is another form of traversal, and it is called post-order traversal. Oh, so why is pre-order good for creating copies, right? So again, so if we were to insert this pre-order, if we were to create a new tree and insert it, it would create this same structure, right? Based on our conditions for going left and going right. However, if we were to take a in order array and insert that into a new tree, assuming the tree is not self-balancing, this is what you're going to end up with, because we're inserting everything that we're inserting always bigger than the previous. So it's, you just got this unbalanced tree. And this is really bad because the advantage of this tree is binary search time. You've lost that over here because we now have to iterate through every node to find the node we're interested in. So now we're back at linear time for searching. So that is something you can use pre-order for, to duplicate, to copy the trees. There's also post-order. And we are at 9:30. We can probably call it here, but post order is what we can use to delete our tree. Because what post order is going to do is it's going to traverse down, it's going to visit the left node, then it's going to come up, and then it's going to visit the right node, then it's going to come up. Won't visit the root yet. It's going to go back down. It was at 21. That's going to go down to 28, and then back up to 25, and then finally 20. So the post order traversal, if we wanted to delete every node in our tree, we could follow the post order pattern and just remove all the leaf nodes, and then you would move everything on the right, and then you remove everything on the move everything on the left, and then move everything on the right. And that would be a post order traversal. And the code is the same, other than, you guessed it right, we would just move this down to the bottom, and now we're doing post order traversal.
Isn't that the entire theorem of a tree? The basic binary search tree?
Yeah, I think we hit on a lot of the basics of it. We didn't go into unbalancing and deleting nodes.
Future us?
Future what?
Future us?
Future us. Yeah, that's our next adventure. All right, I'm gonna wrap it up here just because it's 9:30. And any questions for the people who are, and everyone took off.
So I missed the start. So what was the intro here?
Yeah.
Here.
What did we do in it? Where did you come in? Do you remember?
20 minutes in.
Okay. Yeah, so we went over the basics of just a basic binary tree, having 0, 1, 2 children. And we just blazed through here and looked at some of the basic names of things.
There was no story. There wasn't a narrative. It was, here's
Start
a
coding.
simple mathematical expression, go code it, store it in a tree.
Yep. And that was it. Then
Sorry, there
we
was
wanted to
no
write some
story
code.
problem, Nick. John has a set of numbers in his hand and wants to store them in the most efficient search way. They are unordered.
Yeah.
He has 5 numbers. He can't keep track of them all.
How would he do that? Thanks everyone for hanging.
Thanks for people on YouTube and LinkedIn.
No
You
sweat.
guys should join us because I know you're out there, but we're going to sign off.